Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today my group consists of five people. Will present to you on our group project for BCC DenseNet versus uh, DenseNet plus SVM. So moving on. I will introduce our group member. First of all, in the left section, left image is Muhammad Shafiq Hafiz bin Muhammad Kamil, and the middle one is me myself, Ifana Baby Azizul Hakim, and the right one is Shafiq bin Tajul Molok. And this is on the left is Zulfadri bin Mohtar, and the right one is Sharian bin Shakib Priyono. So I will pass to Sharian to present on our objective for today.
For the objective, we got four different objectives that we achieve from this project. The first one is task definition. What is meant by task definition? It is an image classification which assigning each image to its corresponding BCC categories. The second one is data description. Data description is how we utilize a data set containing 5,970 images for unlabeled basal cell sarcoma and few 318 labeled basal cell carcinoma. And the third one is our evaluation criteria. It is a success of the AI model that will be measured by its ability to correctly classify all the images with their respective categories. And the last objective is the scope of this project, where we are focused solely on classifying basal cell into three types using deep learning models, which is and the combination of DenseNet plus SVM.
Introduction. Deep learning. Deep learning is a subfield of machine learning that focuses on using artificial neural network with many layers to simulate the human brain's learning process. It's designed to automatically discover patterns and features from the large amount of data without the need for human interventions. As you can see on the figure on the left, this is the architecture of artificial neural network. There are three main layers, which are the input layer, hidden layers, and the output layer. In the input layer, data are received from the external source, and then their features will be computed and in the hidden layers where the neural network will learn the pattern and features of the data. In the output layer, the prediction output will be made in the layer. DensNet. DensNet is a short form for Densely Connected Convolutional Network. It's a deep learning architecture for convolutional neural network CNN introduced by a team of researchers back in 2017. It revolutionized the computer vision field by introducing novel connectivity patterns in CNN that address the challenges faced by traditional CNN, such as reusing features, vanishing gradients, and parameter efficiency. Now let's take a look at the architecture of DensNet. DensNet architecture still resembles the traditional CNN, but with additions of dense block and transition layer. Dense blocks are the building blocks of DenseNet architectures. Each dense block consists of multiple convolution layers, typically followed by batch normalizations and nonlinear activation functions, for example, such as ReLU. And each layers within a dense block receive feature maps from all preceding layers as inputs, facilitating features reuse and propagation. Within a dense block, each layer receives the concatenate output of all preceding layers as its input. This is also known as feed forwarding. The pattern will continue for all layers within the block, ensuring a highly interconnected architectures. And for the transition layers are used to connect dense blocks. They serve two main purposes. The first is to reduce the number of feature maps and downsampling the spatial dimensions of the feature maps. This will help in maintaining the computational efficiency of compactness of the network. Supervision is a supervised machine learning algorithm primarily used for classification tasks, but it can also use for regression SVR and outlier detections. While it can handle regression problems, SVM is particularly well suited for classification tasks. Now, let's see how it works. So we have a data points and we want to separate them into different classes. SVM will help us to find the best possible boundary called as a hyperplane, which separates these classes. But it's not just any boundary. SVM maximizes the margin, which is the distance between the closest data points from each class and the hyperplane. These closest points are called as supervectors. They are super important because they define the position of the hyperplane. Now, sometimes data is not simple. It's not linearly separable. That's where the kernels come in. Kernels can help transform the data into higher dimensional space so it becomes separable. So SVM will find the optimal boundary with the widest margin to separate the classes, and if it get tricky, kernel will help to handle the nonlinear data. That is how the SVM works to separate our data into several classes.
I will be continuing with our input data. In our input data, there is a main folder called BCC only or Basal Carcinoma Cell Only. In this folder, there contains all unlabeled images with a grand total of 5,970 images. Next, BCC type. BCC type contains three subfolders that contain confirmed images that have label on them. These subfolders is called type 1, type 2, and type 3. This is what is inside type 1 folder. In this folder, there are images with label type 1 in metadata.csv. In this folder also are cases of basal uh, cell carcinoma superficial. Next, this is type 2 folder. Uh, in this folder, there are cases of basal cell carcinoma nodular. So all of these images are labeled with type 2 in metadata.csv. Lastly, type 3 folder. In this type 3 folder, there are cases of basal cell carcinoma infiltrating. So all of these images are type 3 in metadata.csv. Okay, now I will move on to process data. This is our process folder for BCC. Uh, in this folder, same as in input data, there contains three subfolders for different type of basal cell carcinoma or BCC. Okay, this is our type 1 folder or the cases for basal cell carcinoma superficial. In this folder, there contains 1954 images upon clustering. Next, type 2 folder or cases for basal cell carcinoma nodular, there contains 1367 images upon clustering. Lastly, in type 3 folder or basal cell carcinoma infiltrating folder, there contains 2469 images upon clustering.
Okay, so now we move to the output data. So in output data, we have a density prediction all for CSV file in a CSV file. So this the initial prediction that we get from the images. And once we move to density predictions, not all of them are not all of them are the same as the initial predictions, but most of it is most of the prediction is quite accurate. And now this is DenseNet plus SVM prediction for all in a CSV type file. So as you can see, once we train the model, not train the model, we actually let the model train itself, and this is the prediction that they got, which is the same as the initial predictions. All right, that's all from me. Thank you. So we move to data segmentation, data segregation.
The next thing that I like to talk about is data segregation. Data segregation is where our project dataset will be divided into two parts in the MATLAB. The first one is for the training purposes and the second one is for validation. Out of the 5,970 images for BCC type, 75% of the images, which is 4,373 images, will be used for training, while the remaining 25%, 1,875 images, will be used for our validation and testing.
Assalamualaikum warahmatullahi wabarakatuh. My name is Irfan Nabil bin Azizul Hakim. My student ID number is 20233677749, and right now I'm presenting to you about training phase. So in the training phase, first and foremost is DenseNet deep learning. Here's the coding that I will show towards you guys. So this is generally all regarding the DenseNet deep learning, and then here we specify what's the value of initial learn rate and max support and other stuff. And moving on, this the chart, or what you call is a result or based on the training that we already do it. So as you can see, the training progress, we do it on 8 Feb 2025, and from April 1 to April 10, we get to know the the accuracy of the training. And then moving on, this is the evaluation of DenseNet model performance, where we have confusion metrics, DenseNet, precision per class DenseNet, recall per class DenseNet, F1 score per class DenseNet, micro F1 score DenseNet, AUC per class, and then lastly is micro AUC DenseNet. So this is the performance or the evaluation that we get. And then after that, because our title is DenseNet and versus DenseNet plus SVM. So this is the DenseNet plus SVM. This is where after we do extractions, we train it in SVM. So this is the coding. And then once the coding is successful, it will say SVM model train, and then features extracted, and lastly the evaluations for DenseNet plus SVM model performance will display on the image right here that I show you right now. So we have confusion matrix, precision per class, DenseNet plus SVM, recall per class, F1 score per class, and macro F1 score. And I will pass to my group members, Shafiq, to present his part of demonstration. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Shafiq bin Tajamuluk and I will be presenting about the demonstration and also the conclusion of our project. So first, let's open our MATLAB. Right, so in order to run the GUI, first, most importantly, of course, we need to run the deep learning. So we need to train our machine first in order to detect the BCC. So in our project, we will be using two machine learnings, and deep learning and machine learning, which is first DenseNet, which is deep learning, and also then a combination of both machine learning and deep learning, which is DenseNet and also SVM. So after run the training, it will give two important train model. So the DenseNet and also the combination of DenseNet and SVM. this tool is important in order to run the GUI, because without both of these, um, it cannot detect the BCC and also cannot predict whether it's type 1, type 2 or type 3. So uh, we just load it because I have done it before, and so we will run this to open our GUI to detect to check whether the image is type 1, type 2 or type 3. So first we can see we can choose image whatever we want. So first let's see, we will see this image. Let's see what it predict for this image. As you can see, it predict type 3. It is correct. This BCC is type 3, which is infiltrating. We have the black color, so it is type 3. So the prediction that was made by the machine is correct. So let's check another one. Okay, we just take this. Let's see whether it predict correctly. Okay, it predict type 1. Yeah, this is also correct. This is type 1 because it does not really have the black color, and it's not really the picture is not really that bad, so it's type 1. So that is um, let's see. Let's see. Yeah, as you can see that in this, it predict is an example of what I do previously. It predict for this other image, it's type 1, that is correct according to the train information. And then yeah, also for this example, it's also prediction for this picture is type 3, so it is also correct.
For the conclusion, as I conclude, of all of this project is by using a dataset of 5,970 images, and then we are using clustering to learn features and divide it into three types. This experiment examined the capability of deep learning and combination of both deep learning and traditional machine learning to classify the unlabeled BCC images into the appropriate category, which will be used to assess the performance of deep learning model. This experiment also emphasized the need for more research and development with larger datasets for increased accuracy and also generalizability. While also this project, we are providing insight into AI's potential for our image classification in semi-supervised context. That is all from us. Thank you.